All right, this is a homework problem that I had queued up a while and we didn't get to do in class. So let's just start it out. You can see we have the randomized numbers there in red. So your numbers may have been different. You can always go back and review your old expert TA problems to look at what you did and compare. So starting off, we have the yo-yo is swinging in a horizontal circle, and it makes this angle theta s with the horizontal, and we have a string length that is rs. And so here's our number rs. Our angle theta s we don't know, and it tells us to first of all choose the correct free body diagram. Well, choosing the correct free body diagram, all I really need to do is determine what forces are acting on this yo-yo. So I look at the yo-yo and I say, well, the yo-yo clearly has mass. If it has mass, then it must have a force of gravity. What direction does the force of gravity act? Always, always, always straight down, because that's how we define down. So I have a downward force due to gravity. Yeah. And then I have a string. A string makes a force of tension, and that force of tension is always parallel to the string and going away from the object. So I have a force of tension going like, well, let's make that a little better. A force of tension going like that. Now I need to label these forces. So force of gravity, which is of course mg, and I have the force of tension, which is equal to T sub s according to their notation there in part B. Now you might say, well, there's more forces, but you'd be wrong. What else is acting on this yo-yo? Some people might say, well, there's the centripetal force, but the centripetal force isn't acting on the yo-yo. The centripetal force is the term we give for the sum of the forces acting toward the center of the circle. So these two forces are going to add together to give me that centripetal force. So that's part A. I have my free body diagram. Part B, calculate the tension in the string Ts in units of newtons. So I look at my diagram. I have force of gravity upward, force of tension over here to the right. I am going to start off by saying, let's make ourselves a force triangle using Newton's second law. So I'll start part B down below here. Sum of the force vectors is equal to mass times the acceleration vector. Well, the acceleration vector is toward the center. I know the acceleration is equal to v squared over the radius of my circle. That's, better put the magnitude. The direction is toward the center. V is equal to omega naught times the radius. So I could also say that the acceleration is equal to omega naught squared times the radius. What is the radius? The radius is not the length of the string rs, it's the horizontal portion of the string. If I were to draw the triangle, first of all, for the string, I would have a triangle that, or for the string, a triangle that includes the string and the vertical. I'll start with drawing just the string. So in red, I'll have the string. Here's my string. And now the fun thing is, my string, if I drop a vertical from the string, and if I do a horizontal from the end, like this, and now I've just made myself a right triangle. And we know from what's given that this angle here is defined as theta, theta s. This side here is rs, and this side here is the radius of the circle it's doing. So I can immediately say, well, this is the adjacent side of the triangle for the r, and so r must equal rs cosine of theta s. So that's the r that goes in my acceleration. Now let's look at my force triangle. My force triangle has, surprisingly, or maybe not surprisingly, depending on what you've looked at, a very similar look. I have my force of tension, my force of gravity, and so let me put some arrows on there and some labels. The force of tension, which is labeled tension string in the problem. The force of gravity, which is equal to mg. And then if I add those two together, my resultant is going to be going from here to here. And that resultant is ma equals m omega naught squared r. What's the angle between those two? Well, it's the same angle theta here. So using my Newton's second law, doing a graphical solution, I immediately see that the force S is related to the force of gravity and related to m omega squared r by the angle theta. So let us take the adjacent side. I'd have this side here, so m omega naught squared r divided by the force tension is equal to cosine theta. Now if I substitute my r in there, I'm going to have m omega naught squared rs cosine theta sub s is equal to force tension cosine theta sub s. I just multiplied the force tension across. I can cancel my cosine thetas, and my force tension is just mass times omega naught squared times rs. Now we were given all of those numbers, so just putting these in, my mass was 0.034 kilograms, and my omega naught was 5.9 radians per second. I have to square that. And the radius of the string was 0.42 meters. And so that gives me the force of tension, or tension in the string as the textbook is calling it, is equal to 0.4971 newtons. Now how many significant figures do I have? 2. So the correct answer would actually be 0.50 newtons as far as significant digits go. So there is my solution for part B. I calculate the tension, I have a number. Now part C, calculate the angle in degrees. Well, this can't be that bad. I mean, let's look. I have right here in the triangle, if I use tangent in the triangle, I can relate mg to m omega squared r. So let's just do that. So this is part C. Tangent theta is equal to the opposite side of the triangle, mg, divided by the adjacent side of the triangle, m omega naught squared r. Cancel the m's there, and solve it for theta by using inverse tangent, and I'll have theta is equal to the inverse tangent, or arctangent if we prefer, of g over omega naught squared r. And by r I mean, I should have thought this one through. The problem with doing it this way is that, go back. I should have thought this one through. because r depends on theta. We had r as rs cosine theta. That would have been a bad move because I would have to bring the cosine theta back in. So instead, let's use this relationship that I already created to now find what theta s is. So using that relationship, rewriting the equation, and so putting in my values here, that would be, it seems like I'm doing this harder than necessary. Oh wait, yes, this doesn't work still because I have the r in it. I have to use sine. Sine strikes me as the one to use. Sine of theta s is equal to the opposite side, mg, divided by the hypotenuse, ft. So that's going to be 0.034 kilograms times 9.80 meters per second squared, divided by my force of tension, which was 0.4971 newtons. So theta s is equal to inverse sine of that same thing. And that's going to give me my actual angle. And that is going to give me 42.09 degrees. Now, truthfully, the significant digits when you use sine is slightly different than using other things, right? We didn't multiply, we didn't divide. We actually use the infinite series here. But I will stick with 3 significant digits, so I'll say that's equal to 42.1 degrees. So now, after a few starts and stops, I got my angle. Now I'll go back to read the next part. Part D, Jeremy increases the angular speed of the yo-yo such that theta s decreases to 1/2 of its initial value. Calculate the new angular velocity, omega f. So, I'm going to have to make a new page. I have my new relation. This is D, that theta 2 is equal to theta s divided by 2. Now, from what we worked out before, and by before, it would actually be from what I just finished doing. Let me come back to this. Sine theta s mg over ft, that's equal to mg over, and what did I have for ft? Ft was equal to m omega naught squared rs. So the m's cancel. So this value here, I could have just put g divided by omega naught squared rs. So now that I have a new theta, I have the same string length, I can find the new omega. So I'm going to use that relationship and so I'll rewrite it. Sine theta, and now this sine theta is going to be a general for whatever the angle is equal to g over omega squared rs, where omega is whatever the omega is at the moment. So solving for omega, I'm going to have omega is equal to the square root, since that's omega squared, of g over sine theta rs. So my new angle is theta s over 2, so I'll put 2's here because I'm doing it for 2, and theta 2 is equal to 42.09 degrees divided by 2. So this is equal to square root 9.80 meters per second squared divided by sine 42.09 degrees over 2 times RS. RS is, and I have to look this up here real quick, 0.42 meters. And so popping that in the calculator, I get 8.061 rads per second, which to 3 significant digits again is 8.06 rads per second. Okay, moving on to part E. So looking back at the problem, part E says that Jeremy now has increased the angular speed of the yo-yo such that theta s has decreased to 1/2 of its initial value, same as what I just did. Calculate the new tension on the string using the omega that I got from the previous part. So I just got this omega, and our tension was calculated with, and I'm going to scroll back so we can look at the equation. Maybe. There we go. Our tension was calculated with force tension is m omega squared rs. So force tension is equal to m omega squared rs. So I'm just going to put in my mass, 0.034 kilograms, times the new omega, what I just found up above, 8.061 rads per second, quantity squared, don't forget the square, multiplied by the radius of the string, 0.42 meters. And that gives me force of tension is equal to 0.9279 newtons, or to 3 significant digits, 0.928 newtons. Finally, the last part of the question says, if the increase in the angular velocity of the yo-yo took place over 1.2 seconds, calculate the angular acceleration alpha in radians per second squared of the yo-yo during the increase. So, this one here, surprisingly enough, is probably the simplest one. It was the only part that was really new for this section. We know by definition that alpha is equal to change in angular velocity divided by change in time. So that'd be my angular velocity 2 minus my angular velocity I started with divided by the delta t. So that's going to be 8.061 rads per second minus the 5.9 rads per second that I started with divided by the 1.2 seconds that it took to change the velocity, and that gives me alpha is equal to 1.8006 rads per second squared, or to correct significant digits, 1.80 rads per second squared. Alright, so there we have worked through the entirety of this homework problem. And yes, I did stumble a little bit at one point. I had to get which equation I'm going to choose correct. There are lots of equations you can choose, and sometimes you can get there multiple ways, and sometimes it turns out only one way is really going to be convenient. Alright, so that's my next last problem for the night.